Hello and welcome to the session. So as we have previously represented the program, so to represent the laser, sensor and the rviz.launch file. So yeah, so we'll go ahead further in terms of visualizing this particular output in rviz. So yeah, so over here I've just like made few changes in order to rectify the error. I've just removed all these spaces. So just change the spacing to 2. You can just click over here and then click on here and select 2. So 2 space. So then you can just click on XML. So you will probably see it plain if XML is not visible. So then you can just click on auto detect. It will automatically detect XML. So if not, you can just type in XML here and select XML so that you could get this particular color coding and representation and all. So then after, just save it and run it, and you would see this particular output in ROS. Okay, so I'll just expand this out. Okay, so there's our entire ROS. So ROS is a package or a program which is used to visualize the data. So for an example, a sensor data, maybe a camera data, or maybe you could see it as a laser data or odometry data and all. Okay, so all these kinds of data could be visualized. So yeah, so that's what like ROS is useful for. So just change this fixed frame to fixture. You would see two options. So just select fixture, so which would represent the fixed frame, and then over here click on add. So in order to view the robot, you can just select robot model, and if you zoom in, you can see over here this is our robot model. So the top would represent the laser scanner, laser data, so laser sensor, and the bottom would represent the fixture. So if you just expand this out, you can see the links, two links, fixture and laser sensor, laser or laser sensor. So next click on add, and then after click on laser scan. Okay, laser scan, so which would give you this kind of output. So here we would need to select like we still didn't represent laser parameters, and also that's why we won't get any output. Okay, so we'll represent that laser parameters, so then we'll be able to use this laser scan to look at the I'll say the data. Okay, so let's save this out, and then the rviz file. So in rviz we're gonna make, like in yeah, so over here we represent the program to visualize in rviz, right? So similarly, to visualize the laser scanner in Gazebo, we would need to represent certain code. So that's why you just click on file, save as. Okay, so then change this as Gazebo dot launch file and click on save. Okay, so this is the Gazebo dot launch file. So here the same thing, we would need to represent the version, the launch file, and just remove this entire code, and over here type in param. So here again we need to launch our robot description. So the robots to see the robot in Gazebo, we need to launch the robot description. So type in command equal to cat dollar. So basically like the package location, find laser, sorry, the package name and the file location. So type in urdf laser dot chakro. Okay, so let's close this out. So that completes the representation of loading the robot. So once that is done, so in order to visualize the robot in Gazebo, so we'll just like define the program. So type in node name is equal to let's say like the node name is Gazebo underscore spawn, so some particular node name, and the package name. So the package is Gazebo underscore ROS. Okay, so this is a package which is used to connect ROS with Gazebo. So Gazebo with ROS or ROS with Gazebo, same thing. Okay, so then the type of the package. So type of this package is spawn underscore model. Okay, so this is the type of the package. So next let's type in output screen. So to visualize the output in the screen, so you can just type in output screen. So next let's remove this out, and tap on, so let's type in arguments, args, arguments equal to urdf. Okay, so the robot description param, so let's type in robot description, the name of the parameter, robot description, and then model. So the model name, so the model name is robot, so which we have defined over here, robot. So then after, we need to specify the x and y locations that we want in Gazebo to be seen. So just type in x and type in dollar bracket open argument underscore x. So this argument underscore x represents the location of the robot in x direction. So similarly, I mean in terms of x. So similarly, we need to represent in terms of y and z. So here let's type in y, and let's type in here as z axis, z axis. Okay, so let's close this out. I mean, yeah, so let's close this out. So which completes the representation. So these parameters, argument and all is that, right? So those parameter values, we need to define it out. So define over here, argument name is equal to x, and default, the default value is equal to, let's say 0. So I'll just like represent it to be 0. So similarly, copy this out. Okay, let's close, open the bracket and change this to y, change this to y. Okay, and similarly, let's represent everything to be by default 0. Okay, so that completes the entire code in order to launch the file in Gazebo. So for this, create a new terminal, then source the devel setup.bash file. Okay, so to launch Gazebo, type in ROS launch Gazebo underscore ROS. So this is the package name, and empty world. So to launch a empty space, you can just type in empty world dot launch. So which will launch Gazebo. Wait for a few seconds, and you can see this is the Gazebo world. So in this, we need to launch our, I'll say our robot. So I mean the laser scanner. So for this, we just need to type in ROS launch laser package and Gazebo dot launch file, the file name. Okay, so yeah, so here look, there's an error. Let's rectify that. Argument y is already defined. Just change this to z, and let's rerun it. Okay, so there's an error in terms of this particular code. Unknown substitute for argument x. Okay, let's check it out. Yeah, I'm sorry. Over here, we're not supposed to specify underscore. That's the reason why we're getting that error. Okay, so let's run it. Okay, so now I can see it's running, and you would see the laser scanner over here. Okay, so it looks like it's not visible. Okay, so yeah, so you can see now like the robot is not visible in Gazebo world. So that is because here in terms of the robot, we have defined the pose, the inertia parameters, the visual parameters and all. But we would need to also define other parameters such as collision. So you can see if you just type in model, ground plane, link, and you can see pose, inertial parameters, and collision. Okay, so these parameters we have not defined out, so that's why we're not able to see the robot. Okay, so to define this out, I'll just stop this Gazebo, and over here let's type in the collision parameters. So collision parameters would define, so for an example, there are two bodies, so two bodies would collide with each other, right? So let's say if they are touching with each other, we need to define certain parameters, so that we could look into like representing the collision between two links. So let's type in the parameters that we would require. So let's say I'll just type it over here, tab space, collision. So the collision name is equal to, let's say, fixture collision. Okay, so some particular name. And next let's tap on enter. So here we need to define the mass in terms of the collision. The mass value is equal to same thing, that is 10. Okay, so let's close this out. So the mass parameters, then over here in terms of a collision we need to define the geometry. Okay, so let's copy this out, geometry, and paste it here. Okay, so that completes the collision part of it. So yeah, it's over here. So let's type in collision. So let's save it out. Similarly, let's copy this out and paste it over here so that we don't need to again type in the program. So just change this to let's say sensor, the name, the mass value that we have defined previously is 1. So let's define the same value, and the geometry, also dimensions and all. So let's change this out. Let's rerun it to see if we're able to get our output. So first let's launch Gazebo, empty world, and let's launch the laser scanner later. And now you can see the row, like the laser scanner and the fixture. So this is how we could use, I mean, like we could represent the row, like the laser scanner in Gazebo. Okay. So now if you see we have represented the row, like the laser scanner, we could view the laser scanner, but in order to I mean, like represent the laser scanner data, right? I mean, to represent the like in order to simulate the laser scanners rays and all, we need to represent certain code. So let's type in the code here. So type in here Gazebo reference. So in Gazebo we have this particular reference which is known as sensor laser. Okay. Yeah. So let's tap on enter. And then the sensor type. What type of sensor is it? So just type in sensor type is basically a ray. So a laser scanner would send a data which is ray, right? So we'll just type in laser. So the type is ray, and then here just type in head Hoku, Hokuyo sensor. So that's one, like I mean, like that's one type of a sensor which is present. So we have like different laser sensor, right? So in Gazebo we have this particular Hakuyo sensor, which would represent, like which would depict the behavior of a laser. So this Hakuyo sensor is one type of a laser scanner. So you can just check it out online and give you like the entire detail. So next let's type in the location. So I mean like the pose. Suppose by default everything would be 0, the x and y and z, and also the rotation. So just type in pose. Okay. So then after type in visualize. So visualize is used to visualize the data. So just type in false. So yeah, so I don't want to visualize the data. So for now we'll just type in false and then we'll change it later so that we could like view it out or not. Okay. So next let's type in the update rate. So the frequency at which data is being updated. So let's type in rate 20. So some particular value, update rate. And then in terms of the ray, we need to define the ray parameters. So what is the scan uh, area? What is the length of the ray that would occur and all. So just type in horizontal rays. Okay, so which is horizontal to the plane, and the samples. So how many samples is required? So I'll just type in, let's say, 720 samples, and the resolution of the rays. So let's type in over here resolution. So let's say the resolution is 1. and the minimum and the maximum angle. Minimum angle. So the minimum angle in terms of radians, not in terms of degrees. So I'll just type in as 1.57, that is 90 degrees. And the minimum angle, let's close it up. So similarly, the maximum angle, max underscore angle. So same thing, I'll just type in 1.57, maximum angle. So let's close this out and let's close horizontal. So that defines the race, like the race parameter. And let's type in, like, let's close the scan. Okay, so this defines the ray, and then after we would need to define the range. So what is the distance that the rays should travel? So let's type in range, and over here the distance, let's say the minimum, like we would need to define the minimum distance. So the minimum distance is 0.1, which I'm assuming, like based upon the lasers sensor which you're going to represent, you need to represent the parameters. But I'll just like represent the minimum rays to be 0.1 and the maximum rays to be 10, like the maximum distance that the rays could travel. Okay, so the minimum and the maximum rays. And similarly, the resolution is equal to 0.01 resolution. And let's change the range. Okay, so this completes representation of the ray. So let's close ray. Okay, so now if you see that this completes the dimension, I mean like the parameters that we will need to represent for the laser scanner. Okay, so just type in plugin. Okay, so the plugin name is Gazebo underscore ROS underscore head underscore Hakuyo underscore controller, and the file name is, okay, so lib libgazebo underscore ROS underscore laser dot so. Okay, so I mean Gazebo ROS head Hakio controller is there, right? So that's the plugin which is present, which would like simulate our laser scanner. Okay, and the file name is like this is the plugin and this is the file name. So next, in order to visualize the data, we need to create a topic. So let's type in topic name is equal to scan. So I'm just typing in the topic name as scan. So topic name and the frame at which the data should be shown. So let's type in frame name. So the frame name is sensor laser. So the one which you're representing here, sensor laser. And let's close the frame name. And then after, let's close plugin. Okay, so that completes our plugin and also our sensor. So let's close sensor. And finally, after closing the sensor, we need to close Gazebo. So let's save it out and let's relaunch it in order to visualize the robot. Sorry, the laser scanner. So let's rerun it. Okay, so it just takes some amount of time to in order to launch. Okay, so it looks like there's an error here. So I'll just stop this out. And also let's stop Gazebo. Okay, so let's rectify the error that's present in this particular code. Okay. So I've made like few simple errors. So I mean like the namings were wrong. So instead of representing visualize, I didn't represent ye. So similarly over here, I didn't represent ye. So like that I've just like made few errors. Okay, so I've just updated out, and over here just changes to -1. Okay, so -1.57. So next let's relaunch the empty world and Gazebo. Okay, so now I can see the laser scan. So now if you want to see the output, so just okay, one second. Okay, so now we have seen, like we've got the output, right? So which is a laser scan, like laser sensor. So next, in order to view the also like the output in RVS, you just type in RVS dot launch. So which will launch the laser, I mean like the package. Sorry, I mean like the laser scanner in RVS. So next, select fixture, add robot model, and then add laser scanner, laser scan. So this will be helpful for viewing the data. So then click on scan. So this would be visible. So first you need to launch Gazebo and then like the laser scan, and then launch RVS. Only then this topic would be visible. So now I can see it has updated, and you can see like the parameters and all like this. Okay. And now if you see, there is no data that is being shown as an output. That is because if you see in Gazebo, right? So there are no obstacles which is present. So because of which there is no data that is being shown in RVS. So for that, you can just select this cylinder and drag it and place it somewhere closer to it. So similarly, if you select one more cylinder and select one more cylinder like this, and now if you zoom in, so you can see the cylinders, and if you open up RVS, you can see the obstacles that is present. So based upon the cylinder, this is the region that is detected. So by that way, we could come to a conclusion that there is an obstacle here, here, and here. So this red color dots represent the obstacles. I mean, like the obstacle is present and the rays has been reflected back. Okay. So if you want to see the laser scan data, so I'll just stop this and also Gazebo. So if you just change this to true, save it out, and then if you launch Gazebo, I mean, sorry, if you launch Gazebo empty world and then uh, the robot into the Gazebo empty world, so the laser scan, like laser scan into the Gazebo empty world, you would get an output like this. Yeah, I'm sorry, I have to launch RVS. Let's stop this out. Okay, so I'll just launch the model in Gazebo. So let's stop this out. Gazebo. So once the like the laser scanner is launched into Gazebo, you can see this kind of output. So like this. So this is the distance which the rays are traveling, and this is the scan area, like the minimum and the maximum angle which we have specified. Okay, so next, if we launch RVS, yeah, so after this, you need to change this to fixture, robot model. Let's open robot model. And finally, let's open laser scanner. So here, select the topic which is scan. So next, let's minimize this out. And over here, just drag it and drop it like this. So you can see now, wherever there is an obstacle, the like the data has been reflected back, and wherever there's no obstacle, so the rays keeps on. I mean, like the rays are sending in this are being we'll say is projected in this particular region, but wherever there's no obstacle, so where there's an obstacle, it is reflected back. So if you look at RVS, you'll be able to see the output. So these we'll say the obstacles. So that's how we could represent the also like laser scanner and view the data. So same thing, you could use it in vehicles and represent it out in order for mapping, localization, and SLAM and various parameters. We would represent this sensors, and the sensor data we would use it in order for all these kinds of purposes such as localization, mapping, and all.